Hello everyone. Another somewhat quick tutorial that is relevant on the topic that we've been talking about recently. I want to look at serial bus and kind of contrast and compare different different types of serial buses. This document's a little bit dated. But in some ways it's good because it shows some older serial buses that you may not find in a more current document, and I like that it covers kind of a variety of buses. So we talked about serial bus, a fairly high level, and the serial bus we talked about was specifically UART as the first one that's listed here on this page. But I just want to look briefly at some of the other buses, and this document's up on D12, and I encourage you to look at it in a little bit more detail if you're interested. Okay, so let's look at just an overview of our different serial buses. And when we think about serial buses, there's a variety of different ways they can be connected. Here's an example of an I2C bus. You see the common lines that are connected are SCL and SDA, which stands for serial clock and serial data. This one's actually not, I guess, specific to maybe I2C because it actually shows a separate select line or enable line for each of the slave devices that's being communicated with, which in fact for I2C is not required. The other thing that is quite important when you think about serial communication or any communication over long distances is the difference between differential and single-ended type communication. So the top diagram on the left shows differential signals, and you see that any noise that's in the environment that might be electromagnetic interference or radio waves are in the environment can show up on your signal lines particularly when you have long lines, and can corrupt your data. So a differential signal will use a differential amplifier, which basically takes the difference between the two signals coming in, and any signals that are common to both are shown as VCM in this diagram. So any interference would be common to both signals, and because it's the same on both lines, when you do the subtraction, it gets eliminated, and just the actual data signal is left. Okay. In contrast, on the right, where we don't have a differential signal, the common mode signal, that VCM signal, just is passed through with the actual true data signal, and causes potentially corruption of data. The diagrams on the bottom are showing different types of some different differential signals, not all of them, but really common UART type differential signal is RS485, the first one shown. And again, the signals are transmitted differentially, and it shows the voltage levels between the high and low differential signals. And you'll see they're quite broad, and makes them quite resilient against large noises. And then we'll see LVDS, low voltage differential signaling, IEEE 1394, also known as Firewire, used to be very popular in Apple products. And then on the right we see our single-ended signals, and you'll see there's no difference taken, and we see that the highlighted section in the middle is kind of shown in that orange purple shade, is that kind of threshold level where in that range we are going to be in that indeterminate range that could cause signals to be misinterpreted. And it's also showing our noise margins in there as well. If you look at the output low versus the input low signals, which aren't labeled for all of those, but okay, so I guess just going back to this for a second, you want to think about the environment that your serial communication is happening in, and decide whether you need a differential signaling system or a single-ended. Single-ended are quite common over short distances, and in environments that are not subjected to a lot of noise. Differential is more common over long distances and in environments that might be subjected to large electrical or electromagnetic noise. CAN bus, for example, is another differential signal commonly used in automotive environments or industrial environments, very electrically noisy environments, and therefore differential signal is necessary. I2C, which stands for integrated circuit, is meant to communicate between chips kind of on the circuit board level, not meant to communicate over long distances, and for that application single-ended is fine. Here it's kind of more on in that kind of topic is looking at, on the y-axis, some of the data transmission rates, typical data transmission rates of some of the different protocols. You see I2C down here in orange. Not super high data rates, can get up to I think around 4 megabits, and for pretty short distances. RS-232, a little longer distance if you keep the data rates lower. RS-485 can have huge distances and pretty decent data rates and so on. And then you'll see on the left actually side of that diagram just general purpose logic. So if you just have logic signals transmitted between devices, it's depicting here that these are meant to be over very short distances. Okay, and here's a little bit more detail on some of the data rates or clock rates that some of these various standards operate at. It's actually again, some of this a little bit dated. SPI here is shown as 110 kilohertz, that being the original speed. SPI can communicate up into the megahertz, and often does. USB, this is some of the older USB standards. USB is up into some very high data rates now. In fact, some of the USB 3 standards can have data rates of 5 gigabits per second, and the USB 3.0 or up to even 20 gigabits per second for USB 3.2, and USB 4 is an upcoming standard that is based on the Thunderbolt 3 specification that has come out of some of our hardware developers, and it's looking to support up to 40 gigabits per second data rates. Okay, so again, some of this document's a little bit dated. You see the high-speed USB is showing only up to 480 megahertz, but the I2C 3.4 megahertz is still kind of the upper end of I2C. CAN bus 1 megahertz up until just a few years ago was pretty standard as the highest rate, but now there's CAN FD, flexible data rate that can have data rates up into the tens of megahertz. Here again we'll see some look at the data rates again, but also looking at putting some numbers on the length of the wires that we can have, and also the number of nodes that can be. So yeah, we see some different numbers of nodes that the different protocols can support. CAN being able to support 100 nodes in with the CAN differential. I think it technically can be even more than that, but and some of these standards are just point-to-point communication, and some are able to be daisy chained to support multiple nodes on the network. Okay, so those are other things that you should be considering when you think about what communication standard is appropriate. Okay, UART here, we've talked a fair bit about this, talks about the start and stop bits. Just kind of skim by this because we've looked at this before. Another table comparing data rates and looking at speed versus distance here. So I'll kind of leave the rest of the document for you to explore, see if you find anything interesting. I think some of the more interesting parts are just knowing the names of some of the various communication protocols that exist, and knowing some of the details about data rates and lengths of communication that might be feasible. Actually, let me just stop on CAN here for just a second. CAN, you'll notice that this is not a very good table. Let me grab another example of the CAN protocol packet. Okay, and looking at CAN here, we see that CAN has a huge amount of overhead associated with the data that's transmitted. So CAN can have a data field that's anywhere from 0 to 8 bytes, or 0 to 64 bits. But look at all the other overhead that's in this, and this is just a base CAN format or standard CAN. There's an extended data frame as well. So we've got a start of frame, 11-bit identifier, a 1-bit RTR, a 1-bit IDE, a reserve bit, a data length code that tells us how much data is in the communication, cyclic redundancy check, 15 bits for that, for doing checking of the validity of the data, and some other acknowledge and end of frame data. So we can have over, depending on the size of the data field, we can have over 100% overhead. Part of the transmission that is overhead being that part of the transmission that's not actual data. So and that's a standard data frame, and the extended data frame has an extra 18 bits for the identifier, so even more overhead again. So it's important to remember that when you think about your data rate. So if you just think about the clock that your data is being transmitted at and say, okay, well, I'm going to get my data through at that data rate, while the effective data rate might be much slower because you're transmitting all these extra bits of data along as well. I know I said I was going to let you review this yourself, but lots of people are familiar with USB, and have a look if you're interested. This a little bit outdated on USB. IEEE 1394 is kind of old. SPI, very popular communication protocol, particularly in embedded systems. Very easy to implement. It is a synchronous protocol because it transmits the clock or wires the clock across as well. Typically, the number of connections kind of accumulate because you need a slave select for every slave device on the system. So although you may only have 3 wires for the actual serial communication, you need 3 plus n, where n is the number of slave devices you're communicating to. I2C, also a very popular kind of board level communication protocol for communicating between different peripherals in your microprocessor or microcontroller. Only needs 2 wires, is for short distances, and can support multiple devices. Pretty easy to implement, so something to be aware that it exists. It is asynchronous. There's no clock there is a clock transmitted, but it does use framing bits and incorporates the address in the data packet, such that you don't need to select the device you want to communicate with. The slave devices just look for their address on the communication on the data line when the clock edges start occurring. Okay. Yeah, so again, I encourage you to look at this and even other serial standards. They're very widely used in digital systems and computer systems, and it's very helpful to know when to use the different communication protocols and to know that the different ones exist.